Welcome to the Mahatma Gandhi Institute of Technical Education and Research Center. In 2004, a national level institute MGTA has been started in the field of engineering and technology as per guidelines of All India Council for Technical Education AICTE New Delhi. MGTA is approved by AICTE New Delhi, Gujarat State and affiliated to Gujarat Technological University Ahmedabad, which is also known as GTU. Our goal is to be an institute of generative ideas so that we remain relevant to our society. The MGTA has always been an organization on move with continuous effort on improving its processes and to maintain its relevance to the Indian science scenario, with adding new programs in its programmatic portfolio. We strongly believe in overall development of students, so for that we provide them a different platform like state level tech fest, project fair, different sports activity, which helps students to teach teamwork and problem solving skills to get physical health benefits, boost self esteem, and reduce pressure and stress for prove their skills in distinct area. Welcome to the virtual class of Design of AC Machine. Myself, Professor Gaurang C. Patel, working in MGTA as Assistant Professor in Electrical Engineering Department since 2014. In previous video lectures, we were gone through several aspects of design like stator design, stator core design, length of mean turn, etc. I hope you understand very well all those concepts which I had explained to you in previous lectures. So on the basis of that, today we will going to solve one example which was asked in GTU examination in summer 2019. So let's begin with an example. So in this example, data is given like that. So in this example, a motor is rated with a 15 kilowatt 400 volt 3 phase 50 hertz 6 pole induction motor. I'm talking with this first example, and diameter of 0.3 meter and the length of core 0.12 meter. The number of stator slot is 72 with 20 conductors per slot. The stator is delta connected. So what we have to find? We have to find the value of magnetizing current per phase. If the length of A gap is 0.55 m, the gap contraction factor is 1.2. Assume the mmf required for the iron parts to be 35% of the A gap mmf, and coil span is given 11 slots. Okay. So before proceeding this example, for solution of any example, first of all we have to begin with collect the data which given in the example. So what data we had given? We had given a power that is 15 kilowatt, a voltage that is 400 volt, and 3 phase 50 hertz 6 pole induction motor is given. Okay, so what we have to do first, we just collect all the data what given into the example. Power P is given, power P is given 15 kilowatt. Okay, then it is a 400 volt motor, or also you can consider it as an EB or voltage. Okay, it is a 3-phase motor. Okay, and 50 hertz frequency is given, so F is equal to 50. Then 6 pole motor, that is P is equal to 6. Diameter is given 0.3 meter, diameter D is equal to 0.3 meter, and the length of the core, that is given 0.12 meter. Length of the core, that is given 0.12 meter. Okay, the number of stator slot number of status slots, that is given 72, 20 conductors per slot. Okay, per slot 20 conductor is given. Then next, what data is given, that is the length of air gap is 0.55 m. Okay, length of air gap, length of air gap, which is denoted as Lg, length of air gap which is denoted as Lg, that is 0.55 m. And next thing is given the gap contraction factor. Okay, that is, I'm talking about this, the gap contraction factor. Gap contraction factor, which is denoted as kg, that is equal to 1.2. okay, and else what is given, assume the mmf required for the iron parts to be the 35% of the air gap. So mmf is given as a 35% of 35% of air gap. Okay, and coil span is given 11 slots. Coil span is given 11 slots. So with the help of all those data, we can start the calculation of given example. Okay, so we will begin with the solution. First step, we have to find the slots per pole per phase. Okay, so we are going to find slots per pole per phase, which is denoted as Q. Okay, so Q is equal to how much slots in data they are given. There are 70 slots are given. When you see in the example what we data together, it is shown that is 72 slots are given, pole that is 6, and 3 phase motor was there. So when you calculate it, you will find the answer 4. So will get Q is equal to 4. So the slots per pole per phase is equal to Q, and Q is equal to 4. Then next we have to find distribution factor. Okay, we have to find distribution factor, which is denoted as KD. Okay, so for the distribution factor KD, we have to consider the equation sin Qy by 2 divided by Q sin y by 2. Okay, so the question was immediately asked in your mind, that is, what is y, it is denoted over here. Okay, so y, that is stands for angular slot pitch. That is the angular slot pitch, and we already find the value of Q over here, that is equal to 4. So for getting the value of Y, we have one equation, that is Y is equal to number of pole into 180 divided by number of slots. Okay, so number of pole, how many pole? It is given 6 into 180 divided by 72. So when you calculate this value, so when we put those values, number of poles, that is 6 into 180, we will get 1080 divided by 72. So the answer is 15. Okay, so what we get, Y is equal to angular slot pitch is equal to 15. Okay, so we can write it down, Y is equal to 15, which we already calculated. So we get Y is equal to 15. Okay, then those two values we have to put in the place of Q and in the place of Y. Okay, so now we will put those values. Q is equal to 4 and Y is equal to 15. So when we calculate the KD, which is equal to sine, in place of Q we will put 4 into 15 by 2, 4 sine 15 by 2. Okay, so what we did, we just do the simply put the value of Q and Y in this equation. So KD is equal to sine into 4 into 15 by 2 divided by 4 sine 15 by 2. When we do the calculation for the same, what we get the value. We will do the calculation over here. So for distribution factor KD is equal to, we have the equation and we put the value of Q and Y. So sine 4 into 15 by 2 divided by 4 sine 15 by 2. So when we do the calculation for that, what answer we will get, we will see it. So it is sine 4 into 15 by 2 divided by just a minute. Oh, sorry, I just put it the wrong sign. Divided by 4 sine 15 by 2. Okay, 4 sine 15 by 2. So what the value we got, that is 0.957. so in place of 0.957 we can write it 0.958. okay, so here we get the value after the calculation. KD is equal to 0.958. okay, then we proceed for the calculation of slots per pole. Okay, slots per pole. So simply we have the number of slots, that is 72, and per pole, that is pole is given as 6. So slot per pole we find the value 12. Okay, and coil and span is given is equal to 11 slots. So from those data we can see that how much slots per pole is given. So number of slots are 72 and poles are 6, so there are 12 slots per pole in that stator, and coil span is given as an 11 slots. Okay, so from that we can find the angle of coding alpha. Okay, angle of coding alpha is equal to 1 by 12 into 180. After the simplification we will get the 15 degree. So angle we will found the 15 degree. Okay, so after finding those solution, now we will move towards the pitch factor Kp. Okay, so the pitch factor Kp, the equation for the Kp, that is cos alpha by 2. So what is the value of alpha over here? That is, we found 15. Okay, so that is cos 15 by 2. So when we do the solution, what we will get, we will see it. So we put those values, that is cos alpha by 2, that is cos 15 by 2. So we will get this answer, that is 0.9914. okay, so we just simply write it down, 0.9914, that is the answer which we got, 0.9914, the answer of Kp, which stands for the pitch factor. Okay, now we will find the value of stator winding factor. Okay, stator winding factor. For that, what we consider for the stator winding factor, that is Kd and Kp. So over here we already found the value of Kd. You can see the value of Kd, that is 0.958. okay, the value of Kd, that is 0.958, and value of Kp we just found it here, that is 0.9914. so after calculation we will get the value 0.95. so over here stator winding factor, which is denotes as KWS, that is stator winding factor, KWS, the value of KWS, that is 0.95. okay, so I just like to recall you what up till we gone through. Okay, so first of all we will find the slots per pole per phase, that is equal to 9. okay, so the value of so slots per pole per phase, that is Q, so value of Q, that is 4. Then we found from that distribution factor Kd, okay, with the equation of sine Qi by 2 divided by Q sine y by 2. okay, then we found the angular slot pitch, that is the 15 degree. Then distribution factor Kd, that we found 0.958. then slots per pole, that is 12, and coil span, that is 11 slots. So then after Now we will move towards the next calculation. Then we will find after KWS, that is total stator conductors. Okay, so total stator conductors is equal to stator slots into conductors per slot into conductors per slot. Okay, so value of stator slots, that is 72, and conductors per slot is given 20. Okay, so we will find the answer, that is 1440. Okay, so the total stator conductor, that is 1440. Then after, we have to find the stator turns per phase. Okay, that is stator turns per phase. So stator turns per phase, which is denoted by TS, that is TS is equal to total stator conductors divided by number of phase into 2. So when we put those values, that is total stator conductor, what value we get? 1440 divided by number of phase is 3 into 2. So solution of this, that is 240. Okay, after that we are interested to find flux per pole. So the equation for that flux per pole is, just a minute, flux per pole, which is denoted by phi m flux per pole, that is EB divided by 4.44 F into TS into KWS. Okay, F into TS into KWS. So we have to put the value of all those terms, that is EB, that is the stator voltage per phase, EB, that is the stator voltage per phase. So stator voltage per phase is given 400, value of EB is given in the data. Okay, then 4.44 F, that stands for the frequency, which is 50. Then value of TS, we just found the value of TS, that is stator turns per phase, that is the value of TS, that is 240. So over here it is 240, and the value of KWS, which we were found over here, value of KWS, that is stator winding factor. Okay, value of KWS is what? 0.95. Okay, so after making the calculation of all those data, we will found the answer 7.9 into 10 raised to minus 3 Weber. Okay, so if you want to make the calculation, you can simply calculate it into the calci. Okay, I will just show you how it will be calculated. Okay, so simply you can calculate like that. The value of EB, that is 400 divided by 4.44 into 50 into 240 into 0.95. okay, so the what value we will get, that is 0.00790. okay, so when you convert it in form of 10 raised to minus 3, you just have to multiply by it 1000. So you can simply write down that is the value 7.90 into 10 raised to minus 3 Weber. okay, so how it comes, you understand? So here we write it down, the value which we got, that is 7.9 into 10 raised to minus 3 Weber. okay, then after we are interested to find area per pole. okay, now area per pole, area per pole is equal to pi dl divided by p. okay, so over here d, that is the diameter of motor, and l, that is the length of core. okay, so we just simply put the pi into d, that is stands for the diameter of motor, and diameter of motor which is given 0.3 meter, and length of core, that is, just a minute, length of core is given 0.12 meter. okay, and the number of pole that is given in the example, that is 6. okay, so when you calculate this value, you will find the answer 18.85 meter square. okay, so would you like to write me down what is d and l? okay, then I will write it down. Look over here, that is d stands for diameter of motor, and L stands for length of core. So you might be not getting confused what is D and what is L. P, that you obviously know, that is number of poles, and what answer we will get over here, area per pole, that is 18.85 meter square. okay, then next we will find average air gap density. okay, that is average air gap density. So average air gap density, which denotes BAV, is equal to phi m divided by area per pole. okay, so well, we found the value of phi m, that is flux per pole, that was found 7.9 into 10 raised to minus 3, and area per pole, that what we find 18.85 meter square. okay, so over here we can simply write down the values what we found during the calculation, that is 7.9 into 10 raised to 3 divided by 18.85 into 10 raised to minus 3, that is the area per pole we just found out over here. 18 area per pole, that is 18.85 meter square. okay, so after calculating those values, we will get 0.418 Weber per meter square. So the what we found over here, that is the average air gap density. okay, average air gap density, that is BAV, average air gap density, that is 0.418 Weber per meter square. Okay, then next we will find gap flux density at 30 degree from pole axis. Okay, gap flux density, gap flux density at 30 degree from pole axis. So for that is Bg at 60, that is given as 1.36 BAV. Okay, so BAV, what it stands for? BAV, that is average air gap density. Okay, average air gap density. So 1.36 into BAV, that is 0.418. The calculation will gives a value 0.57 Weber per meter square. What you do, you just do each and every calculation by yourself. Okay, so you make it understand how it will come. Okay, the value of BG60, that is 0.57 Weber per meter square. Then we will find MMF required for air gap. Okay, MMF required for air gap, that is MMF required for air gap, that is ATG, is equal to 8 lakh into BG60 into kg into LG. Okay, this is the equation for the MMF required for air gap ATG, that is 80,000 into BG16 into kg into LG. Okay, so BG60, that is the gap flux density, what we found right over here, that is BG60.57 Weber per meter square. Okay, kg, that is gap contraction factor, which is given in example, that is 1.2, and Lg, that is the length of air gap, that is equal to 0.55 mm. This both data kg and Lg is given in the example, that is kg is given 1.2 and Lg is given 0.55 m. Okay, so over here we just put those data simply for the calculation. Okay, BG60, that is the gap flux density, what we found 0.57, then kg, that is the gap contraction factor, that is 1.2, and Lg, that is the length of air gap 0.55 m. Okay, so just a minute. So in place of 0.55 m, we just have to write it down, 0.55 into 10 raised to minus 3. Okay, so after making the calculation, what we will get, you would like to do it in calci, so I will show you how it will do in the calci. Okay, let's say I will show you. Okay, so for the ATG, first of all, what we are doing, put the value 8 lakhs into 0.57 into 1.2 into 0.55. Okay, So when you get the answer 300960 into 10 raised to 3, that means divided by 1000, so what you will get, that is 300.96. so we can write down, in place of 300.96 we can write down 301. Okay, so after the calculation what we get, 301 ampere. Okay, then after finding the mmf required for air gap, we will move towards the mmf for iron parts. Okay, so for calculating mmf for iron parts, we have the data given in example, that is in data that it states that, what data states that mmf for iron parts, mmf, just a minute, mmf for iron parts given 35% of the air gap mmf, given 35% of air gap mmf. So simply we can calculate, we just found out the value of air gap mmf, that is mmf required for air gap. So we can calculate in this way. Okay, mmf for iron parts, mmf for iron parts is equal to what it's given, 35%, so we can make it 0.35 into mmf required for gap. Okay, so when you put those values, 0.35, just a moment, 0.35 into 301 into 301, where 301 is came from, that is mmf required for gap, that is the value of atg. Okay, 301, we will found that 105 amps. Okay, so mmf for iron parts, that is 105 amps. Okay, so total mmf at T60 is, we can say that total mmf, that is ampere turn at 60-degree angle, which is equal to mmf required for air gap, mmf required for air gap plus mmf for iron parts. Understand that? We just found out both the values, that is mmf required for air gap and mmf for the part of iron. Okay, so consecutive value, that is 301 plus 105, so it turns to 406 amps. The answer is 406 amps. Okay, so then next, what we are interested to found finally, our aim is to find the magnetizing current per phase. Okay, our aim is to find magnetizing current per phase. So for that, all the required data we found that. Okay, the equation for the magnetizing current per phase, that is Im is equal to 0.427 into P into ampere turn at the 60° into gap contraction factor into number of stator slots. Okay, so all the value right now we had. For the simplification, I just write down KW stands for stator winding factor, stator winding factor, TS, which stands for stator turns per phase, stator turns per phase. Okay, so the what is the stator winding factor value of stator winding factor KWS, that is 0.95, and value of TS, that what we found stator turns per phase, that is 240. So when we simply put those values over here, that is magnetizing current IM is equal to 0.427 into P into 8060 divided by KWS TS. Okay, so we just put the value of all those data, 0.427 into P, that is number of pole, that given 6. 8060, we found the value of 8060, that is ampere turn for air gap, that is 406. KWS, that is stator winding factor, you can see that KWS, that is stator winding factor, which is 0.95 into 240, that is stator turns per phase. Okay, so finally when we do this calculation, we will get the answer. What answer we will get, I will just show you in the calculation. Okay, so finally we will do the calculation for magnetizing current per phase, that is 0.427 into number of poles into 8060, that is 406, divided by KWS, that is 0.95 into TS, that is 240. Okay, so the answer is 4.56 amp. So we can simply write down this answer. So we can write down this answer, 4.56 ampere as needed, or we can say that is the value of magnetizing current per phase, that is the value of magnetizing current per phase, 4.56 ampere. Okay, this is the final answer, magnetizing current per phase, that is equal to 4.56 ampere. I know this is the lengthy example, but it needs practice. More and more practice, you will be easily solve this example. So for your better understanding, I will show you the simplification of that solved example, so you can refer during the calculation. Okay, so here I quickly recall this example, that what we solved step by step. Okay, so first of all, we just found out the distribution factor KD with the help of this equation sign. Okay, then we are going to find angular slot pitch, that is 15 degree. Then distribution factor KD, that is 0.958. Then slots per pole, that is 12. Then we found pitch factor Kp, that is 0.9914. Stator winding factor KWS, that is 0.95. Total stator conductors, that is 1440. Then stator turns per phase TS, that is 240 stator turns per phase. Then stator voltage per phase EB is given 400 volt. Then flux per pole, for finding the flux per pole, 5M is equal to EB divided by 4.44 FTS KWS, which is the equation. When we put all the values in this equation, we will get the answer 7.9 into 10 raised to minus 3 Weber. Then after we will find the area. We found the area per pole, that is pi dl by p. Over here the value of pi dl by p, we just put it down, and simply after the simplification we will get the 18.85 meter square. That is the answer for area per pole. Okay, where d is equal to diameter of motor, that is given 0.3 meter, and length, that is length of core, is equal to 0.12 meter, which is given in example data. Okay, then average air gap density, which is denoted by B average. The value of average flux density we will found 0.418 Weber per meter square. Okay, then we found the gap flux density, that is 0.57 Weber per meter square. All those calculation I simplified in detail in the video lecture. Okay, then we found MMF required for air gap, that is ATG is equal to 8 lakhs into BG60 into kg into LG. Okay, so BG, kg and LG, which stands for gap flux density, gap contraction factor, and length of air gap, all the values are given in the example. That is kg, that is 1.2, LG, that is 0.55 m. Then after we will found MMF for iron parts. Okay, so the MMF for iron parts, that is 0.35% of the given air gap MMF. So the answer of MMF for iron parts, that is 105 amps. Then total MMF 8016, that is ampere turn at the 60 degree angle, that is 406 ampere. Then magnetizing current per phase, that is what we require to found. For that equation is 0.427 into P into ampere turn at 60 degree angle divided by KWS into TS. So when we put all those values, KWS stands for stator winding factor and TS is stand for stator turns per phase. So when we put all those values in this given equation, we will find the answer 4.56 ampere as a magnetizing current per phase. Okay, so I hope you understand this example very well. So please keep practicing this example, because it is so many times asked in GTU examination. They are just change the data, but the pattern is same. So once again I say that more you will be practice, more you will be get in touch with this. Okay, thank you very much.